Hi, welcome to part 3. I'm just trying to prove that if big F is defined to be the integral of little f along a smooth curve from a fixed point z0 to z, then big F prime is equal to little f. And I've worked it down I need to compute this integral along this blue line L, and I need to show that the integral divided by delta z, which is the length of the line, is going to be less than epsilon for this fixed epsilon. And I think we're in the home stretch. So I actually don't want that yet. This is equal to the length of the integral f of w minus f of z, which is a constant as far as this integral goes, because the constant is with respect to dw, divided by the length delta z. And now, we've seen this before, if I take the absolute value of an integral, I can replace it with less than or equal to the integral of the absolute value, f of w minus f of z dw, and this is still going to be over delta z. Okay, well, now I can do another bigger than or equal to. Any integral is bigger than or equal to, or is less than or equal to the length of the curve times the maximum value along that curve. So the length of the curve here, well, it goes from z to z plus delta z. The length of the curve, well, maybe I'll write this in another step, times the max w belonging to L of f of w minus f of z, which is just the integrand. F of z, remember, is a constant, divided by delta z. Okay, well, the length of L is clearly just the magnitude of delta z. That's nice because it's going to provide some cancellation. Times the max of w belonging to L of f of w minus f of z. Those cancel, I'm just left with the max w belonging to L of f of w minus f of z. Okay, we're just about done. So what do I have? I want to show that this derivative is equal to little f. This derivative is roughly equal to this quotient minus f, and this whole thing is equal, less than or equal to, less than or equal to, less than or equal to the max of this. But here's the key. The key is that little f is holomorphic, which means little f is continuous. If it's continuous, that means there exists a delta such that if delta z is less than delta, then it's continuous. That means all the values close to it, I wrote that wrong. It should be w minus z less than delta implies f of w minus f of z has to be less than epsilon. That's by continuity. That's exactly what continuity says. So this epsilon here is the same as the epsilon I have up here. So I can pick a delta such that as long as I'm close enough, then w minus z is going to be less than epsilon. So I get that this thing is less than epsilon if I pick to be close enough. How can I make that? So I can make delta z, right? W's, remember, lie along this line. So as long as delta z is within delta, then it works. So for delta as in the continuity box down here, so in other words, as long as this delta is the same as this delta, we're good. Why is that? Well, as long as we're in this delta, as long as we're close enough so that the difference between f of w and f of z, every point along this line is less than epsilon, I get that this quotient minus f of z is going to be less than the maximum value of the distance. But we picked the maximum value. We picked delta z to be close enough so that the maximum value is less than epsilon. So we're done. We proved it. We proved that f prime of z is equal to f of z, because that's just the limit of this thing, and it equals that because I can show that the difference is less than epsilon. We are done. Fundamental theorem of calculus is proved.